very different directions beyond physics that Shoucheng is interested in the recent years. So we are very happy to have a very special speaker, Brian Zhang, as our first speaker. As you all know, Brian is Shoucheng's son, and I want to give a brief introduction. Brian did his undergrad in Harvard in physics in 2011 to 2015, and he worked 2 years in DeepMind 2015 to 2017, and after that he started his PhD in Oxford in computer science. So and also he gave this nice summary of Shoucheng's recent interest beyond physics, which is the algorithm for the future, which is the title of this session. So now Brian will share his thoughts and experience with us. Thanks.
What do I speak into? Do I speak in? Just this is fine. Okay. Hi, you heard Xiaoliang's introduction. So the presentation I'm going to give is not really what I'm researching. So I'm doing a PhD in algorithms for analyzing genetic data. But instead, I just wanted to take this opportunity to prepare a more high-level talk and one that tries to unify my father's different interests. The title is quite long, but hopefully it will get a bit clearer as we progress. Okay, so yeah, as Xiaoliang introduced, besides my talk, here are 4 of the other talks that we kind of introduced into the workshop. And I think it was actually Eugene Demler's suggestion after seeing some of my dad's writings to say, you know, it would be great if we could have some presentations on these other areas. So we heard yesterday morning from Shafi Goldwasser. She wasn't able to make this afternoon, which is why she presented yesterday. And then we will have 3 other talks following mine. Yeah, one might ask, you know, what unifies these different areas that Shoucheng was interested in? And one answer to that is, you know, they could really only be unified in the mind of Shoucheng. He really, like my sister said, I think 2 days ago or 3 days ago at the memorial service, you know, he saw connections between the first line of Anna Karenina by Leo Tolstoy with the second law of thermodynamics. So really, you know, his mind stretched very far to see different areas. He might say himself that the kind of his motto of unifying these was "in math we trust." You know, all these areas, including his physics, are based on simple mathematical principles. But I want to focus in on, well, I guess, sorry, first I would like to say that, you know, all these kind of areas were, in some sense, a reason that he got into VC work. I always felt like for him, being a venture capital partner at Danhua Venture Capital was an area for him to hear about all these exciting areas of current research. And, you know, he could ask really the dumbest questions he wanted to and just force people who are pitching their company to him to give him an explanation. But today I want to focus in on maybe drawing more of the connections between these areas in physics. After me, Shoucheng will talk about machine learning and materials discovery. So this is an area that's, you know, also has a deep connection to physics. But I'm going to kind of try to tell my own narrative that ties together some of my father's interests with condensed matter physics. So, you know, his training was in condensed matter physics. That was the area he worked in and the area he loved. And what are the principles from condensed matter physics that we can take and apply to the wider world? So if we think about what is the fundamental principle of condensed matter, one could say it is the statement by Anderson in '72, more is different. So we know the physical laws that govern, or of quantum mechanics that govern individual particles, but when we bring them into collective situations, the behavior can change. And that's, you know, the great interest that he worked in and that many of you are interested in. So, you know, this area of many-body science has already been applied to some other systems like the brain and other real-world networks. But let's think not just on condensed matter in general, but try to draw some connections between the particular area that he worked in, which was topological insulators and states of matter. So this brings me to like the big question, which we will try to explore. So if topological insulators are formed from the collective behavior of atoms and electrons, then if you take real-world economic agents, what happens when you combine those? Another way of saying this is what might be the topological phases of collective human behavior. Okay, so the talk will be a little speculative, but we'll try to address some of these areas of other algorithms that my father might have been interested in. And I do think that he really believed in this unity, and that was what brought him to touch all these and read about all these different areas. So if we want to ask about how my dad might have thought about this, you can actually look at some of his slides for an example. So these are all images that were in some of the slides he presented. I added this photo of superfluidity. So he would often present this slide saying that in maybe a regular conductor, even though things are flowing, there is resistance. So this, he would draw an analogy to human beings, which all have their preferences. They're all trying to get somewhere. But if the conditions aren't right, you'll end up with a traffic jam. Whereas the ideal is to create these states where people or particles can flow either dissipationlessly or flow just very fluidly. So and here are the examples of some of the three famous phases of matter that you all work on. So yeah, I think this is one answer. The essence of these materials is that they allow really fluid flow and collective movement. And so my dad did believe a lot in economics. He believed a lot in the principle of Adam Smith's invisible hand, which is saying that in the free market you allow things to perfectly match supply and demand. So that's kind of one connection to economics. But let's look even more specifically at the topological insulator. And so so I'm going to pick out one particular area in topological physics that we might be able to apply. So this is the idea of what I call like topological robustness. I think Shoucheng said this is more or less accurate. So in the quantum Hall state, so both of these materials are in a sense robust to impurities, and that's very important when we actually want to design these and realize experiments. So in the quantum Hall effect, even if you have an impurity on the edge, and I think Laughlin was the first to discuss this, the flow will kind of just go around the impurity. In the quantum spin Hall state, what happens is, this is an illustration from a Physics Today article by Shoucheng and my dad. So because, I won't be able to explain it as well, but if there is an impurity, if you have some backscattering, and there's no magnetic field, I think, the spin 1/2 particle upon reflection gets a minus sign, and that creates a perfect cancellation, which means that the phenomenon is somewhat robust to impurities. So that will be all the physics. So I'm kind of trying to lift this idea of robustness, and let's see how we can apply it to economic systems, shall we? So the idea is to connect condensed matter physics with the area of algorithmic economics. So you have multiple agents, and how do they form some collective behavior? In particular, we're going to think about this idea of robustness, which in this case was robustness to impurities. But there's no perfect analogy to economics, but there are three examples that I will present, and maybe it can just get people thinking. So the first area, I will discuss the stable marriage problem. So that will be the next slide. So I'll tell the story when we get there. The second is a condition of truth-telling in the second price auction. And the third is this idea of decentralization, which shows up in the BitTorrent protocol. So these are all very different ideas, but my dad, he was definitely very interested in the stable marriage problem and BitTorrent. I think not as sure about the second price auction, but I'm going to try to unify these all and kind of deliver a talk that I think my dad would enjoy. So let's get into it with the first part, which is the stable marriage problem. Okay, so the stable marriage problem. So yeah, Sun Xiaoqi actually mentioned this in his in one of the speeches he gave yesterday. Yeah, so I see him. So several people were wondering what this is. So now is a chance to kind of go over it. So in the stable marriage problem, it was proposed in the 60s. You have a set of men and a set of women, and they each have preferences with who they would want to marry. So person 1, their preference is first person C, then B, then E, then A, then D. And person A, their preferences are first person 3, then 5, then 2, then 1, then 4. And so you want to marry these two groups. So you want to create matchings. And you want a stable marriage, a stable matching. So an unstable matching is what happens if they're, so I'll just, okay, so you've matched everyone up, but the matching would be unstable if there exists a person in, like a man and a woman who are not currently matched to each other, who would prefer to be matched with each other than with their current partner, okay? So, you're mapping 1-to-1. Yeah, so both the, so let's try to do an example. Okay. Okay, so I've drawn a few lines. So it gets a little bit confusing, but let's just take this dotted line between number 4 and between 4 and C. Okay, so 4 is currently matched with B, and then C is currently matched with 1. Okay, so in this case, like 1, their top choice is C. So this person, this man is very happy with this woman, C. But this woman, her order is 4, then 3, then 5, then 1. So she would prefer to be with 4 than with 1. And furthermore, 4 is currently matched with B, but B is their 4th choice, whereas C is their 2nd choice. So even though this man loves this woman, she would rather be with him, and he would rather be with her than their current matching. Okay, so this is an unstable matching. So this is no good, right? So it encourages cheating and affairs. So we want to try to find a way to solve this. Okay, so the stable matching is one in which you can do the match so that you have a robustness, you have a stability. Okay, so when this problem was proposed in 1962, the authors also proposed the deferred acceptance algorithm. So I will sketch the deferred acceptance algorithm. I won't prove why it is the true matching, but it's not too difficult. So you cycle between 2 steps, and we're going to do the case with men proposing. And you might ask what happens with if women propose, and we'll get to that later. So you cycle between 2 steps. In the first step, unengaged, so you have 2 states, either proposal or engagement. So first, unengaged men propose to their most preferred woman, whom they have not yet proposed to. Okay, so let's do that step. So here you take the men, and they each figure out their first preference. So 1 is C, 2 is A, 3 is D, 4 is A, and 5 is A. So they each propose to their first choice. Okay, so red is the proposals that they have issued. So now it goes to step 2, which is the woman. So the woman, in this case, basically the women just choose to get engaged to their best proposal that they've received. So A has received proposals from 2, 4, and 5. They look at that, and out of those, their favorite is 5. So A will choose to be engaged to person 5. B doesn't have any proposals, neither does E. And C and D each have 1 proposal, so they're going to accept that. So blue becomes the engagements. So these 3 people have accepted they have made engagements. So now we go back to step 1. The unengaged men propose to their most preferred woman, whom they have not yet proposed to. So now these 2 people, they don't have anyone, so then they will go down their list. So before 2 proposed to A, now 2 will say, I'm going to go with my next best choice, so I'm going to propose to B. 4 proposed to A, and they're going to go with their next best choice, which is C. So now they have issued 2 new proposals. Now it goes back to the woman. So now B will accept this proposal because it's their only proposal. but now C gets a choice. So C was previously, blue means engagement, so C was previously engaged to person 1, but upon inspection they see that now they have a proposal from person 4 and they actually prefer person 4 over person 1. So they will break off the engagement to person 1 and become engaged to person 4. Okay? So now they broke off the engagement. Now person 1, it's their turn again. They had proposed to C, so now they propose to their next best person, which is B. B looks and they rank between 2 and 1, and they see that they prefer 2, so they reject person 1. So 1 proposes again. So now they propose to C and B. Now they propose to E, and then E says, you know, that's my only proposal, so they accept the proposal. So now everyone is, the algorithm terminates, and then you still need to prove that this produces a stable marriage. I'm going to leave out that proof, but this is the algorithm. Okay, so hopefully that wasn't too fast. So this was proposed in 1962 in this paper, College Admissions and the Stability of Marriage. And even though this seems like a very simple idea, this won them the 2012 Nobel Prize. I think Roth has is currently at Stanford. And so, you know, they looked at the problem of college admissions, which is slightly different because every college can accept multiple people. But this can also, so this can be used in the setting of admissions. And in fact, if you have friends who have done medical residency, that's kind of how it works. You submit your preferences, you order them, and then there's this match algorithm which will then spit out, they just match you to one school, so you don't get a choice. But there's a centralized algorithm that does everything, and it has other applications as well. So now we'll just interrogate the question a little bit more. Okay, so the first question you can ask is, are the stable matchings unique? Are there multiple stable matchings? And the second question is that the Shapley, Gale, deferred acceptance algorithm, there's a broken symmetry. So in this case, men do the proposing and women do the evaluation. So what if women propose instead? Okay, so we can actually answer both of these questions. The first question, the answer is that actually many stable matchings can exist. So the Gale-Shapley algorithm gives, which I outlined, gives one stable matching, but there can be many out there. Okay. And then, so you can also do a version where the woman proposed as well, and it might give you a different stable matching. And furthermore, if you consider all the stable matchings out there, it turns out that with the men proposing, out of all the stable matchings, they get the stable matching that is best for the men. Okay? So if the woman propose, they can get a better stable matching. So what I've shown in this slide is the stable matching we deduced earlier if the men propose. And you see A, for instance, is matched with 5, who is their second choice. But if the woman propose, if you look at their preferences, A's first preference is 3, then 5, then 4, then 1, then 2. So if they propose, they'll make all the proposals, and then they'll all get accepted in one step. And so the women all get their top choice, and the men don't get as much their top choice, but it's still a stable matching. So it turns out that the gender that proposes, this you need to prove as well, but they attain the global optimum for that gender. So the stable marriage problem, it was formulated in the 60s. It is not as considerate when it comes to settings like gay marriage, which you can analyze with other things like the stable roommates problem. But it does show us that the current system of men proposing is a sexist system. So we have gained some new knowledge from that. Yes, there's always at least one stable solution if you have 2 equally sized sets. Yeah.
So there can be more than one stable solution?
Correct. Yeah, there can be multiple stable solutions. The men proposing algorithm finds one of them that's best for the men. The woman proposing finds one that's best for the woman. Okay, so I'll try to speed up a little bit. So let's say that you've set the problem so that you know that the men are going to do the proposing and the women are going to do the accepting. So it turns out that the woman can actually collude. So the men, it's in their interest to report their true preferences, but you can actually imagine a setting where the women might all get together and say, like, hey, if we were running this, we could do it better. So we're going to misreport our preferences and then collude. So this is the intro to one of the, so I've kind of touched on the first idea, which is stability. So the second topic we'll talk about is truth-telling or truthfulness. So in this setting, the men have an incentive to be truthful. They want to tell their true preferences. And so if you can assume that you can get the true preferences of the woman, this is a good algorithm. But this is not, like, it actually is not the best incentive for the women to be truthful. Maybe individually, like one of them, it's still the best interest to tell the true preferences, but if they all got together, you could break it. So now I'll move on to the second example I've proposed of robustness. So this is the truth-telling problem. This one I won't go into as much detail. So this, the example I'll give is from auction theory. So you're trying to bid on something, and one proposal for how you do the auction is the first price sealed bid auction. So in this auction, everyone will bid a value in an envelope. You'll open the envelopes, and then whoever put the highest number on the envelope, that person buys the piece, and then they have to pay that much money. Okay? So let's say you value something at $5, and you're doing this auction. So what should you place as your bid? So you should reason that this is like the auction setting. I value this at $5, and if I'm going to the auction, I want to try to profit off the auction. So you don't actually want to bid $5, because if you bid $5 and if you win the auction, that means you have to pay $5, but you're not actually getting anything out of the auction. So instead, you might say, like, you would bid something like, maybe you bid $3. So then what you're saying is that if I win the auction, I'm only paying $3, and then I get $2 of profit. But then the downside to that is maybe someone else will bid $4, and then they'll get the piece instead of you. So then you'll say, maybe I'll bid like $4.1. And so in actual auctions that have this setting, there is a game theory problem where you have to figure out what are the other people thinking, what are their valuations. But if instead you use the second price auction, in this auction, everyone puts their bid in an envelope. They open the envelopes. Whoever has the highest bid is guaranteed to get the item, but they pay the second highest bid as the price. Okay? So now if you value it at $5, you actually want to just put your true value. So if I bid $5, if I win, that means someone else bid less than me. So maybe they bid 4.5, and then I will win and pay, or I will earn a profit of $0.5. So this was all quick. This is on the second price auction. The second price auction helped Vickery share the 1996 Nobel Prize. And auctions are very ubiquitous in online ads. eBay did at one point use a second price auction. And this is just illustrating the general idea of trying to encourage people to report their true preferences. And this is quite important, because if you want to trust that an algorithm can aggregate everyone's behavior and produce a good outcome, you want to incentivize people to tell the truth. OK, so real briefly, this slide. The whole area, so these two examples of the stable marriage problem and auctions fall into this area of mechanism design. So this is kind of a framework within game theory that talks about these problems. So the key idea is that the agents submit some information v1 to vn, which then gets aggregated and then produces payoffs. But the agents know what the mechanism is, so they might have some incentive to change their thing v1 or vn. So what I was talking about was the property of a truthful mechanism. And then this earned a Nobel Prize in 2007. OK, so I've outlined these two examples of maybe a robustness and a many-body economic system. Now I'll go on to the last example of decentralization. And this is not quite related to mechanism design. It's kind of its own standalone concept, but it does fit into this broad field of algorithmic economics. OK, so the algorithm or protocol is the BitTorrent protocol. So here there's a movie or something, or maybe less contentious, some big file on a centralized server. And all these people want to get access to this kind of big file download. But early on in the internet, downloading was very slow, and you didn't want to burden one server with all this workload. So I don't even need to really explain the whole protocol. It kind of becomes intuitive. The idea is that you don't want to burden a single resource. So you first split off parts to the other machines, and then these machines will kind of share those pieces within each other. Okay? So you split the file into chunks, you download it from the other computers on the network, and so by using the BitTorrent protocol, you consent to let other computers on the network download from your computer, and by making your computer available, you actually achieve faster download. So it incentivizes people to participate in this network. It was proposed in 2001, and it's very successful. So yep, it's an example of peer-to-peer file sharing. So it doesn't overwork a central server. The downloads can actually be faster because you can find a computer that's closer to you rather than on the other side of the globe to do the downloads. It's robust too if a single computer in the network or even the centralized server, if it were to crash, you can maybe dynamically find other computers to get the uploads from. And then the last question we might ask is, what about if there are people on the network behaving badly? You know, this is another example of like, if you decentralize it, you want to make sure there is this robustness property. So we need to introduce one more idea. So the setting would be like, let's say I'm trying to read, let's say I'm in the White House and I'm trying to read this important document, but some other government wants to like, give me the wrong document. So what if they just like hijack the other computers and then they serve me the wrong document? So what you do is each chunk here, which is illustrated with a little color, you, when you advertise this file is available on the BitTorrent network, you compute a kind of a hash. So you compute a summary of each of the chunks. So it's kind of like a checksum, but it has the property that the checksum you can compute it one way, but it's very hard to generate another input that has the same checksum. So in this way, you can do the computation. You kind of get all the pieces, and then you can check against the global file descriptor to check that you got all the right pieces. OK, so decentralization is actually a really key concept. And this was just a simple example. All the examples I gave are quite simple. But if you combine this idea of decentralization or distributed computing with an idea of privacy, you can actually achieve, you deduce the framework of secure multi-party computation. So Shafi talked about this yesterday. If you combine the idea of decentralization with this idea of consensus, so you want everyone on the network to kind of come to the same conclusion, you actually get the idea of blockchain. And so a lot of work is needed to do to make sure you're robust against malicious actors on the network. But the idea of the blockchain is you have one distributed consensus, and then you can really democratize a lot of activity that's done today. So instead of having a central bank, which keeps track of money, you distribute it, and kind of there's no need for that. And so this is kind of like one final example of robustness. So in all these examples, you're trying to avoid different temptations of human behavior. So in the stable marriage problem, you're trying to avoid cheating. In the second price auction, you're trying to avoid lying. And in decentralization, you're trying to avoid the corruption of power. Okay, so you want to kind of spread things across and not have to trust any centralized authority. Okay, so then I say maybe blockchain. This is obviously something that my dad was very passionate about. And it still is a difficult concept to learn, but I encourage everyone to think about that and maybe spend some time with these concepts. So yeah, I think I'll end there for questions. Yeah.
Thanks, Brian, very much for this beautiful talk. Yeah, I'm sure Shoucheng would love to hear. And questions?
So in the large n limit, for example, I mean, yeah, right. For when there are a lot of people, so I guess the number of stable matching is actually measure 0 in all the random matchings, for example. Is that the case, or?
Yeah, I would guess so. And then the algorithm is O of n squared in the time complexity, so it doesn't take too long. It will terminate.
And so you briefly mentioned the collusion part, actually. So doing the collusion, people can tell the truth or not tell the truth, right?
Yeah.
So does that in general make their algorithm faster or slow down the procedure of finding their stable matching?
Yeah, I think it's always the same time complexity, which is like, or it's usually like a worst case of n squared. It could be faster. And I think it would always roughly fall into that category.
Brian, it was a very nice presentation. Thank you for doing this. I have a question. So you presented as topological robustness, but we know that you don't always need topological robustness. You can have emergent universal phenomena, right? Often like pattern formation in classical physics. To me, frankly, this looks more like maybe there are some universal emergent phenomena, but they don't rely necessarily on something geometrical. So, but maybe you have something else in mind.
Yeah, I think there is like a wider area of intersection between like condensed matter or statistical physics and these like large-scale networks. So I think people have done a lot of other research on like emergent phenomena. There's this thing called scale-free networks, and people I think try to do some like renormalization problems on these like networks. So I didn't go into that in this talk, but I think that's another connection. I was trying to come up with some more like new material in this talk.
So my daughter recently went through the medical residency matching. So was it in her interest to not reveal her true ranking, or
good
in
question.
that case?
Yeah, I'm not entirely sure about how it works, but from the point of view in this case, the men are doing the proposing, and it's in the men's incentive to tell the truth. So if you assume that you can get the true preferences from these people, and in this case, if the men are the I think, they make it so that the students are doing the proposing. Yeah, that is how they do it. So a lot of these people who worked on these problems, they designed the algorithms themselves. Alvin Roth actually extended the residency matching program to handle couples, because there also is a process for matching couples together.
So in these distributed sharing cooperative co-distribute in the decentralized system with sharing data, how are there people figuring out better ways to represent improvisational agency, or what agency is? Because you said voting and auctions and so forth, but is there like a study of agency? What do you guys mean in this distributed decentralized system of agency?
Yeah, I think it is made so that anyone can kind of propose transactions at any time. And then you the idea is like one person proposes, and then you want to get the whole network to agree on what's been done. So blockchain is just proving that when I spend money, like eventually everyone on the network knows that I spent that money and comes to an agreement. So you can't have individual agency.
I think in last month, Google converted from second price bidding to first price bidding. Is there a mathematical study of maybe under what circumstances Google is expected to make more money out of this conversion or something?
Yeah, so this was a simplified presentation of auction theory. For a long time, Google wasn't even doing like a strict second price auction. I think people think that if they converted to the first price auction, Google actually makes more profit. So that would be one reason for them to convert to it.
This isn't really addressed to you, but to everybody here. I think it would be really appropriate if the physics community adopted something like the match for postdoc applications, and I just want to propose that here. This seems to be the appropriate venue.
Thanks.
The postdocs.
Why only postdocs?
Thanks. Okay. I actually have a quick question. So the BitTorrent case, you also need to you want the robustness. You want it to be like robust against some bad nodes. And the similar things in blockchain, you want it to be robust against attacks. But is there a qualitative difference? Like why one is, you said it's decentralization plus consensus, and the other one you don't call it consensus?
Yeah, I don't know blockchain myself too well. I know there's a lot. So, the thing that introduced the blockchain was this idea of Nakamoto consensus proposed by Satoshi Nakamoto in like 2007. And so there are actually proofs that like consensus is never fully possible under all conditions. So you need to like kind of change the condition and just make it like close enough so that like if 50% of people I think collude on the blockchain, they can still like harm it. but you just want to create the incentives that instead of like colluding on the blockchain, instead they would rather spend that money mining Bitcoins. And so like that's how it balances out. Yeah. So I think some other work needs to be done. It's not as simple as this case, but I don't exactly know why. Yeah.
Okay.
Mining also is basically wasting resources. But anyway.
Yeah, and then my dad was interested in, like, there are other types of consensus that don't, so that's called proof of work, I think, and there's other things called proof of stake that don't waste as much resource and is a bit greener. Yeah.
Okay, considering the time, let's thank Brian again. Where is the next speaker?